Hello, welcome to the University of South Florida's Master of Science in Electrical Engineering for Professionals capstone project for summer 2014. This will be a comparative review of 3C-SiC based semiconductor components versus silicon based components as used in power electronics. Project team members include Daniel Simons, AJ Patel, Anand Rampadarath. Dr. Steven Siddall will be our coordinating advisor. Dr. Farakides and Dr. Hoff will be our technical advisors. Silicon-based semiconductors have been the industry standard for many years due to their reliability, efficiency, and ease of fabrication. There have been several technological advances in the semiconductor technology over the past 2 decades, one of which is silicon carbide semiconductors for high field and high power device applications, in particular for harsh environments and certain bio, nano, and MEMS applications. This project will focus on the cubic form of SiC, commonly known as 3C-SiC, and we will review power electronic components demonstrated with this material and their comparative performance to the silicon-based counterparts. A power supply for an avionics system or medical device will be designed using 3C-SiC, and the system specifications compared to the comparable system using Si technology. We will conduct a comprehensive literature search that will identify mainstream usages for 3C-SiC devices compared to silicon-based components. We'll highlight current system technologies and technologies that have not incorporated SiC but could benefit from the properties exhibited by 3C-SiC. We'll utilize published in-depth characterization, including material analysis and calculations of key performance factors to compare 3C-SiC and silicon side by side to identify some selected applications that would benefit substantially from using 3C-SiC. Ultimately, we'd like to create a device model for use in simulation software such as MATLAB and or PSpice to ultimately achieve the capability to employ 3C-SiC models within a circuit design. In the end result, we would like to design an advanced power supply system using 3C-SiC components and compare its performance to Si components. Then we will simulate using the above device model. Our project goals are to conduct a circuit simulation with the created 3C-SiC device model and analyze the model on the basis of performance characteristics. We're going to select a device of interest and select device parameters for comparison within the model to be built, and provide a comprehensive, detailed analysis that shows the outcome of the literature search, device modeling design, and simulation results that highlight the merits of 3C-SiC. Here's the timeline that we're up against. We hope to have a completed project by August 14th, 2014. All members of the team will take part in conducting material physics studies of silicon carbide, identify a system to simulate, generate a device model, and analyze and present the data accumulated. So some of the benefits of 3C-SiC components include smaller size, higher operating temperature, faster switching time, larger breakdown voltage, reduced cooling requirements, and component reduction in circuit design to achieve the same result compared to Si. As we will be looking at power supply units, we'll be taking a look at 3C-SiC Schottky diodes. Then if we have time permitting, we'll take a look at 3C-SiC MOSFETs. Here's a side-by-side comparative of the material properties for silicon and 3C-SiC. The band gap for 3C-SiC is twice as large of that of silicon. It also has an order of magnitude higher for the saturation drift velocity as well as the breakdown electric field strength, which gives rise to believe that this is a far more superior material to use for high power applications. This table illustrates the doping concentration, electron mobility, depletion area width, and specific on resistance as a function of breakdown voltage. As you can see in 3C-SiC, the depletion area width is considerably smaller than that of silicon. Here's a simple structure model of a power Schottky diode. Here's the IV characteristics for a 600 volt 20 amp Gen SiC Schottky diode that is currently in production. This is for forward bias as temperature changes from 25 degrees C to 175 degrees C. We will use this simple 100 watt power supply unit as a stepping stone for a more complex power supply unit. We'll begin by utilizing the existing silicone components in the power supply, run simulations, and gather data. We'll replace those same diodes with 3C-SiC components, also again run simulations, and then compare the data. I'm Daniel Simons. I received my bachelor's in electrical engineering from the University of South Florida with honors in 2007. I was subsequently commissioned in the United States Navy, and I am still currently on active duty with over 16 years. I became a helicopter pilot upon my commissioning and specialized in the area of anti-submarine warfare, utilizing state-of-the-art equipment to detect, localize, and prosecute underwater threats. My current assignment is Program Manager for Navy Region Southeast Navy Wounded Warrior Program. My current interests include power electronic efficiency studies and research in multipath sonar detection in shallow water coastal environments.
I'm Ajay Patel. I have a bachelor's degree with honors in physics and microcomputer electronics from the University of London in the UK. I currently work for General Electric Healthcare as a systems engineer, primarily responsible for the implementation and design of radiology imaging software and systems.
I am Anand Rampadarat, and I am currently a lecturer at the Anton de Kam University of Suriname, located in my home country, Suriname, South America.